Continuing with section 4.1. So in the last video we stopped after doing example 2. So now we look at example 3. It says let the set B be the R2 set, the plane with following operations. So now we are going to define a new addition or multiplication, or we could have one of them same and the other different, or we could have both different. So here we are saying that the addition is going to be defined as, if we have one vector x1 y1 and the other is x2 y2, then when we add them we will get x1 plus x2 as the first component and y1 plus y2 as the second component. So if you notice, this is the usual addition of vectors that we have learned or seen. But look at the scalar multiplication. So this is saying c times xy is going to be cx, and the second coordinate will be 0. So this is a different kind of scalar multiplication. So we have to check that it is a vector space or not. So we start looking, we can do something we did earlier, one of the problems, that we start looking from the first, axiom number 1, 2, 3, 4, and so on. But the thing is, if you notice that the addition is kind of same, right? Addition is same as in the usual addition or standard addition. So probably we want the first 5 proper conditions or first 5 axioms will be satisfied. Yeah? So we can start looking from the 5th axiom maybe. Yeah, first 4 will be satisfied, definitely. 5th we can check, and then we can, if that works, then we can check the next one and next one. So what will happen here, so if we want to see, so 5th axiom is we want to see if there is a vector u, then is there a vector negative u such that u plus negative u should give us the 0 vector. So 0 vector is the 0, 0. So let's see. So what is negative u? So u, if u is, again you have to kind of pick a u. You have to come up with whatever the coordinates you want to pick for u. So when you say u, let u be a vector in there, and then you have to define that u is equal to what? A1, A2, or do you want to call it x3, y3 like they did, or you can even pick x1, y1 for it. Just put any variables. So now when you do negative 1 times u, when you try to find negative u, how do we find negative u? Remember up there we saw that the last condition was, one of the properties of the scalar multiplication was that negative u means negative 1 into u. So when I do negative 1 into u, then according to this scalar multiplication, which is defined here because we have to use that scalar multiplication, this one. So I will get negative x1, but here I will get a 0. And then if you add u into negative u, you will not get the 0 vector, right? Why? Because you will be getting x1, y1 plus negative x1, 0. So this is the u and this is the negative u. So when you add u into negative u, you are going to get 0 because x1 minus x1, because the addition is usual, so we will follow this addition technique or this addition formula. So the first component gets added into the first component, so you get a 0. The second component gets added into the second component, so you get y, so which is not the 0 vector. Therefore, the inverse does does not exist. Okay, so or you can say vectors do not have inverses. Okay, so the next thing is subspaces of a vector space. Now this is something we already learned or went over in section 2.8, so you can read the definition if you want, but it was very simple that if H is a subset of a vector space, so now we will say if H is a subset of a vector space. So in section 2.8, because we talked about only subspaces of Rn, right? So we said let H be a subset of Rn, and then we define the subspace. But here we say let H be a subset of a vector space V. So the set V is a vector space, and we are taking a smaller set inside that vector set, big set V. So if H satisfies these three properties, first is that the 0 of V is in H. So the 0 vector must be in H. And the second is if you pick any two vectors and add them, the resultant vector is in H. And if you pick any vector and multiply it by any real number, and the vector is still in the set, we say that that smaller set is that H is a subspace. Okay, now theorem 1, this is also, we saw it in section 2.8. So it says that if you have a bunch of vectors, however many, doesn't matter, 3, 5, 4, 2, 1, and so then if you think about all the other vectors which can be written as a linear combination of these bunch of vectors, then that set will be called, is called span of these vectors. Then that will be a subspace. And we actually, if you recall in 2.8, I showed you that we did it with the two vectors, so and which can be extended to any number of vectors. Then example 4, let W equal to xy such that xy is greater than or equal to 0. So this is the set. W is a set of all vectors of in R2. If you notice, this is in R2. So in this space, and the condition is that the product should be greater than or equal to 0. So what does that mean? It means this can happen only when x is greater than or equal to 0 and y is greater than or equal to 0, or when x is less than or equal to 0 and y is less than or equal to 0. So this means we are in the first quadrant, and the second means we are in the third quadrant. So now this is our space. So this is the region. So we are including the axes. Equal to sign means the vector can be on these axes. So if think of it, is it a vector space? So we start from the beginning. If we have two vectors in this space, in these regions here in the third quadrant or in the first quadrant, both of them in the first quadrant, both of them in the third quadrant, or one in the first quadrant, one in the third quadrant, and we add them, will we get the vector back in our one of these quadrants? So, for example, if I pick U to be 3, 2 and V to be negative 5, well, I cannot have a positive 2 over here, right? But let's say negative 2. So if I put a negative sign with one component, I have to put it in the with the other as well. So we can have both positive or both negative. So now when you add them, when you add the U plus V, what will you get? You get negative 3, 0. Is that in the set? Well, where is negative 3, 0? It will be, so negative 3 means we are on the x-axis is negative 3 and then 0. Yeah, so this is this vector, this is on this set. But what about if my U is okay, so if I take the U to be 3, 2, but I am going to take this V to be negative 5, negative 1. So now what will happen? The U plus B will become negative 3 and 1. Negative 3 and 1, which is in the second quadrant, which is not in this region. Right? This vector will be over here. Negative 3, 1, something like this. So which means the sum is not every sum is in our set W. Therefore, it's not a vector. So why not a vector? You can give this example. You can say let U be this and V be this. Then U plus V is not, you get negative 2, 1. Yeah, sorry, this was negative 2, not negative 3, which is still not in the set. So we say W is not a vector space. And if you want to write it in a little bit professional language or a fancy language, you can say W is not a set because it is not closed under addition. Okay, next example, consider the vectors of the form S, X, Y, right? And where X, Y are from R, X and Y are real numbers, so which is our usual way of writing. So S, we could say, is a subset of R2 because this is in R2. So maybe S is a subset, and we may not be able to say that S is the whole R2, but it looks like maybe a subset of R2. Okay, and now we are going to define a different kind of addition. Look here, addition is defined as when you add x1, y1 and x2, y2, you are getting, the usual addition says that you should have x1 plus x2, y1 plus y2. But note here, it is switched. So the result which should be here is going in the first place. And the result which should have been in the first place is going to the second place. So this is not the usual addition. But if you look how is scalar multiplication defined, That is fine. That is our usual scalar multiplication. So now when you check the step by step, you will see that one of the addition property is violated. So let's check. So let's say our u vector is x1, y1, v is x2, y2, and then maybe w is x3, y3. I don't like this naming vectors like this. I like more like u is u1, u2, v is v1, v2, w is w1, w2. Okay, I like, but it's your choice, and it doesn't matter what name we pick as long as we have the same rule. So if I am naming it like this, so my u plus v will be like this. So I'm using this u and this v. So it will give me u1 plus v1, and then here u2 plus v2. Okay. Now, so will this be in the set? Yes, because these are all real numbers. So sum of real numbers is a real number. So these will be in the real number. So this vector is in R2, in S. What about the second property? It's saying commutative law. So can you see from here I can write it as v1 plus u1, v2 plus u2, because real numbers commute. So now I can rewrite it as v1, v2 plus u1, u2. So which means v plus u. So second property is satisfied. Okay, what about the third property? So third property is basically we have to show this. U plus v plus w is equal to, and that's what we are going to check, u plus v plus w. Okay, so we check the left hand side. So v plus w. So what will be v plus w according to this? So it will. So we are adding v1, v2 into w1, w2. So which is going to give us not the usual addition. Remember, usual addition will give us v1 plus w1 in the first place, but in this addition we are going to get v2 plus w2 here and v1 plus w1 over here. Okay, now we add u to this. So u plus v plus w. So this will be u 1 v1 plus this vector, which is v2 plus w2, v1 plus w1. So now this first, the top sum, which is going to be u1 plus v2 plus w2, is going to come in the second place. So you will say u1 plus v2 plus w2. And the second sum will go in the first place. So here we will get u2 plus v1 plus w1. Okay, so we'll leave it here and now we'll do the other part. So for the other part, I have to start with u plus v, which will be, we know it's going to be, because u is u1, u2 plus v1, v2. So we get u2 plus v2 and u1 plus v1. And now I have to add w to it. So u plus v plus w. So it becomes u2 plus v2, u1 plus v1 plus w1, w2. So this is going to give you u1 u1 plus v1 plus w2, and then u2 plus v2. Sorry, we got it wrong. No, it's correct, right? It's correct. u2 plus v2 plus w1. And now if you compare these two, they are not the same. So we say u plus v plus w is not equal to u plus v plus w. Hence, the property fails, and so we can say that W is not a vector space. Not a, vector space. So this is how we do these problems. Yeah. Now there is one more left. Let me do it in the next video.